Hi everyone. I thought I'll discuss the solutions for tutorials and put it up for you so that you can refer to them before the exams. So this circuit, you're supposed to find the input referred noise for this circuit. So first what we will do is, it's just a replication of n identical such stages, and here we are interested in finding what is the input referred noise power at the input. So to solve this problem, we'll just have to find the input referred noise of a single stage amplifier. It's given that the input pair has a transconductance of Gn, and the gain of this amplifier, I'm just drawing the differential half circuit. So this is ground, this is differential ground. Okay, this node, I have actually shown this node is actually at ground, AC ground. Okay, now the gain for this circuit is actually Gn by Gp. Okay, Gp is the transconductance of the PMOS. So now gain is given to you, so Gp is actually Gn upon A. To find the input referred noise, we will find the input referred noise of the half circuit and multiply it by 2, because we will assume the other half will also contribute to the same noise since they are identical and independent of each other, so we can add their power spectral densities or powers. Now for an input referred noise in this architecture, for the NMOS, okay, there are two ways of finding it. You can first you can actually find the total current. So both the MOSFETs actually inject, I'll call it INN and INP. Okay, INP is square, their noise, so we'll use power. So both these MOSFETs are going to inject some current at the output node. So I'll just write it as INN square plus INP square times R out square. The output resistance seen at this node square will be equal to your VN out square. Now INN and INP, we'll write the expressions for them, but before that I want to find the input referred noise. So VNI square, the input referred noise for the single stage, will simply be VNO square, the noise of it, divided by the gain square. Now we know the gain of this amplifier is simply Gn into R out. That you can very easily show that the gain with a minus sign. Okay, but I'm just looking at the magnitude of it, so it is Gn into R out. So what happens here is that when I divide it, your total input referred noise, when I divide it by the gain square, this becomes equal to INN square plus INP square into by Gn square. Okay, so VNI square equals INN square plus INP square plus by Gn square. Now INN is the input referred, the noise of the input, the input NMOS pair, so that will be 4 kT gamma Gn plus Gp is because of the load, that is the PMOS current noise. Divide this by Gn square, so what you will be left with is 4 kT gamma by Gn plus Gp by Gn into 1 by Gn. Okay, so now there is 1 plus, I'll write it in this way. So if I take 4 kT gamma by Gn common out, you'll be left with 1 plus 1 by A Gn. Okay, you'll be left with, I'm sorry, there is no Gn here. Okay, so it's just 1 by 1 plus A. So this is the input referred noise for a single stage. Now you actually have, we have the system, the circuit shown below, they have cascaded n such identical stages. So to find the overall noise, we can apply the principle of superposition. All the noise powers, because they are identical for all the individual amplifiers. So first we'll refer, for every amplifier we'll find the input referred noise, and then individually we will add their powers at the input. So this is the power spectral density for the first stage. So if you look at here, the first stage noise is as it is added to the input. So first stage noise will come, I'll call Vn1 square as the first stage noise. Okay. Now if I call this is stage 1, this is stage 2, stage 3 and so on till n stages. The second stage noise I'm going to call it as Vn2 square. Now when I refer it, the gain of this amplifier is I refer it to the input, it's going to get divided by this first stage's gain. So it will be Vn2 square by A square. And similarly for the third stage gain, it's going to be referred by A power 4 because I have to refer it twice. I have to refer it first to the second amplifier's input and then back to the first amplifier's input. So I'll have Vn3 square by A power 4 and so on. Okay. So eventually it will be Vnn square divided by A power 2 into n minus 1. Okay. So if I substitute n as 3, I'll be getting 4. So 2 into 2n minus 2 or 2 into n minus 1. So this result, if I take, since all these amplifiers are identical, Vn1, Vn2 are all input referred noises of the individual amplifiers. They are all equal in magnitude because I'm assuming that they are all independent and identically distributed random variables, or the noise is same for all the amplifiers. The noise statistics is same, so spectral density will be same, but individually the noise will be different in time, but the statistics are same. So the power spectral density will look the same. Okay, so it will be the squared average of the noise, that Vn square will be the same. So if I'm going to take, I'll call it as Vn1 square. I'll just assume it's all same. So it will be simply Vn1 square into 1 plus 1 by A square plus 1 by A square the whole square plus so on plus 1 by A square into n minus 1. Now this is a geometric series, okay, and we have n terms in it. So I can write it as 1 minus 1 by A square 2n by 1 minus 1 by A square. Okay, and if I substitute Vn1 square, it is 4 kt gamma by Gn into 1 plus 1 by A or 1 plus A by A. Okay, so this can further be reduced as 4 kt gamma by Gn into, now the denominator will be A square minus 1 by A square into 1 plus A by A. So actually you'll actually have 1 plus A by A into A square by A square minus 1. So A and A cancel out, you'll be left with 1 plus A will cancel out with this and you will have A minus 1. So you'll be left with A by A minus 1. Okay, into 1 minus 1 by A power 2n. Now for large number of stages, if n is very large and infinity or n is very large, then this value will simply reduce to 4 kt gamma by Gn into A by A minus 1. Okay, now if you increase the gain, so this result simply tells you that if you look at this result, most of the noise is only because of the first stage itself. Okay, that's what this result tells us. Most of the noise is because of the first stage. It's actually 4 kt gamma by Gm into, the first stage noise is actually 4 kt gamma Gm into 1 plus 1 by A, which is A plus 1 by A. Now this term also, if the gain is sufficiently large, we can very easily show it approaches the first term. So A by 1 plus A, this whole term A by 1 plus A by A minus 1 can be approximated as 1 by 1 minus 1 by A. This can be approximated as 1 by 1 plus A for small values of A. It will be 1 by 1 minus A, the whole inverse. Okay, it will be a big series. Okay, but it can be approximated to 1 by 1 plus 1 by A. So you can say that for large values of gain, this value will approximate it to Vn1 itself, Vn1 square itself. So if your gain is large and you cascade a large number of stages, then the first stage noise will be the dominant noise in the overall chain. So that's why when you design for noise, you have to focus on the first stage being, the noise of the first stage will get amplified. So you can also look at it this way. If you look at the n stage amplifier here, the noise of the first stage Vn1 at the output is going to be amplified n times, it's multiplied a power n times, into factor 2. This is power spectral density, so I should write a power 2n times, which is why it's very critical. The first stage noise is the most critical one for overall noise, so you'll have to burn more power in the first stage to reduce noise. So again, we discussed how do we, so here you can look at this expression and see that to get low noise I have to have high GM, high transconductance, and that high transconductance is obtained by burning more power. So that's it about the first problem in the tutorial. I'll very briefly discuss even the second problem. We have already discussed this in the class, but I'll just discuss this again. Okay, so in this circuit you're supposed to find the gain across V0. To solve this, of course you can use KCLs and KVLs, but we'll simply use principle of superposition. So first I'll analyze this half of the circuit and then later this half of the circuit. Okay, so first we'll analyze this half of the circuit. So if this is AC ground, this is AC ground, we've applied VI here, VI here. So in this circuit, if you see, this stage is a common drain amplifier, this stage is a common source amplifier. It's given lambda equals 0 and gamma is the body effect, both body effect coefficient, and both of them are 0. Okay, so I'll apply superposition. So first I'll find the common drain configuration. The gain of a common drain configuration, if R0 is infinity, is simply equal to 1. We have already discussed this in single stage amplifiers. It's simply equal to 1. So VA will appear as it is. Now to find the gain of the other guy, so I'll just have to ground this and find the gain from VI to V0 to this point. Now this is a common source configuration. The input transconductance is GM and the load resistance is 1 by GM, and source body effect is ignored, so it will be with a minus sign. It's a common source, the gain is with a minus sign, so you will get a gain of minus 1. So this will contribute to minus VA, so you will get 0 volts. So when you apply both the inputs, both VA and VA are present, you are going to get 0 volts at this point. So this part of the transistor, from this there is no contribution from VA. So the circuit is going to look something like this. This is that due to VA there is no contribution. Now there is VA here. So then now I'll find what is the contribution of this VA to the output. So this is whenever you are finding one output, we can ground all the other outputs and try finding their contribution. Now since we are grounding all the other outputs, this node is connected here, the looking impedance here is 1 by GM, right? So you are just looking into the source. This transistor doesn't matter, VGS is 0 and R0 is anyways infinity, so I'll simply replace this whole part by 1 by GM. Now this circuit is actually like a source degenerated MOSFET. Okay, now the looking up impedance here is 1 by GM, and you are taking the output at this point. Okay, now if you look at this circuit, in this circuit the gain of this circuit is actually from here to here. This is a common source configuration with a source degeneration. So the transconductance is going to become GM by 1 plus GMRS, so GM by GM, it will be GM by 2. This will be the effective transconductance after doing the source degeneration. Again, you should know this already. Whenever you do source degeneration to a MOSFET, okay, the transconductance of this device reduces. What I mean by transconductance, apply a voltage VI, I need to find the short circuit current flowing through this. That will be I. Then that term I'm going to call it effective transconductance G. If your RS value is G or RF value is 0, the effective transconductance G will be simply equal to GM of the MOSFET. But because there is a finite RS present, you can very easily show that the transconductance will reduce to GM by 1 plus GMRS. Ignoring R0. Okay, so here I'm going to get GM by 2, the effective transconductance. Now that is going to flow through 1 by GM with a minus sign because it's a common source configuration. Drain is drain is in opposite phase with the gate, so you will get a gain of minus half. Okay, so this VA is going to contribute minus half VA at this point. Okay, Now we are supposed to find the voltage across this device. It's not just the drain voltage, but drain across this device. So you are supposed to find what is the voltage at the source as well. Now at the source, the voltage is simply going to be, if I apply Vi at this point, at the source terminal, the voltage will simply be Vi by 2. Again, you can show this very easily. The source voltage, again you can use Gm by Gm plus Rs is the effective Gm, that is the current which flows through resistance of Gm by 1 plus Gm Rs into Rs will be your Vs, the source resistance, times Vi. Okay, this will be the source resistance, source voltage, and since Rs equals 1 by Gm, you can show Vs is equal to Vi by 2 in this case. Okay, so we have the scenario like this. The MOS voltage, this is at Vi by 2, this is at minus Vi by 2 due to this guy. Okay, now we'll try to find the contributions to the other two transistors. Okay, I've applied Vi here, this is AC ground, and I've applied minus Vi in this problem. We just discussed in the last problem, a few moments ago, when we try to find the gain. So when you're trying to find the contribution from the other two guys, you have to ground this. Okay, now you should see that the looking in impedance, you're looking into the drain of a MOSFET, so this is also grounded. So therefore, if you're looking at the drain, its resistance is obviously infinity, because this is like a source regenerated MOSFET, but since you're looking to the drain with R0 of infinity, the intrinsic gain of the amplifier is infinity. So it's like a cascade stage with a source regenerated with a source regeneration, and anyways you're going to see an infinite resistance at the drain. Now the gain from these two transistors, here it's going to be Vi. From the first stage, it's a common drain configuration, it will transfer here, and from here to here it will be minus of minus Vi. So you'll actually have 2 Vi because of these two guys. Okay, so now there is already Vi by 2 because of this guy, so you'll have to add all the voltages. So 2 Vi minus Vi by 2 is going to be 3 by 2 Vi. That's the voltage because of these three guys at the drain. And again, none of the voltage will leak. I mean, if I drive, this mode voltage will not create a voltage here because R0 is infinity. Okay, so there is no transmission from here to here, so we can ignore that. Now the voltage here at the drain terminal is 3 by 2 Vi, so we know the voltage finally at the drain terminal it is 3 by 2 Vi, at the source terminal it is Vi by 2. Okay, so the voltage across drain to source is just Vi. So your V0 equals Vi, so the gain of this circuit is just 1. Okay, so I'll stop at this point. We'll discuss the solutions for the remaining problem. The remaining part of the solution I'll try to upload it soon. Okay, I'll stop now.